We present multimodal trajectory prediction via topological invariance for navigation at uncontrolled intersections. Multi-agent behavior prediction is a challenging task due to its high sample complexity and interactions. Estimating plausible future of a single agent is already a difficult task. But when we estimate multi-agent trajectories, the solution space is exponentially large. For navigation as a downstream task, we would like to predict a few possibilities that are globally consistent. Our insight is that underlying structures stem from rational agents exist. Constraints such as interactions to avoid collision, geometry of the road, will remove unrealistic configurations. We leverage these structures to capture globally consistent modes. We define a mode as a compact representation for configuration by where and how agents move. For the question of where, we infer intention in location. For the question of how, we infer how agents are passing each other. Formerly, we employed winding number to define how a pair of agents pass each other. Winding number is an accumulation of relative rotations between a pair of agents. Let's look at an example. Suppose we have two agents crossing an intersection, the red agent crossing first, and the blue agent crossing later. The figure of relative position in the middle shows that they're relatively rotating clockwise, and the winding number becomes negative as in the figure on the right side. Now let's consider another case where the blue agent passes first. Then the direction of rotation becomes counterclockwise, and the winding number becomes positive. The sign of winding number shows the direction of relative rotation, while the magnitude reflects the geometry of configuration. And we are applying our framework in uncontrolled intersections. They're common but challenging, since they involve close interaction without explicit communication. Now we propose Multiple Topologies Prediction, a framework of multimodal behavior prediction for navigation. In order to model the interaction effectively, we convert trajectories into graphs and use GraphNet in our model. Each agent's position and velocity become a vertex, and relative position of an agent pair becomes a directed edge. Then we first predict mode signals. In detail, we employed beta variation autoencoder to learn a latent variable to reconstruct the mode signal. At inference, we draw a fixed number of samples from the latent distribution to generate multiple mode signals. And then the future trajectories conditioned by the mode signals are predicted. On top of MTP, we build a navigation framework MTPnav. Once we have candidate configurations, we evaluate those and select the best one to follow. We use a PID controller to follow the equal trajectory from the best mode. We evaluate our framework in single agent behavior prediction task and navigation task. For the trajectory prediction task, we predict trajectories of all agents, but evaluate on the equal agent trajectory. Our method achieved the lowest error, and we decide to run a navigation task with our framework. In navigation, we compare our method with autopilot and MPC with different numbers of agents. This example shows navigation with 3 agents. The blue agent in south is the equal agent controlled by our model. The other 2 agents are controlled by autopilot. The minimap shows the positions of the agents in last 15 frames. The predicted trajectories are shown as circles, and the selected trajectory is in red. At this moment, 3 vehicles are slowing down. Then the equal agent is yielding to another agent, and later it speeds up once the intersection becomes clear. We set collision rate and time to complete as metrics for navigation, and our framework outperforms other methods by large margin. In summary, we propose a multimodal behavior prediction based on topological invariance and outperform in both behavior prediction and navigation tasks in uncontrolled intersections. Thank you.